Hello everybody here. So we'll be starting up with the module 3 of our curriculum, which once again is a continued part of module 2. So what we did in module 2 is we just checked up what are the basic components that we can be using in the digital circuit, how do we connect them, and what is an expression, what are the different forms of an expression, and what are the different methods that are used to reduce the expression. So this is a brief blow up of what we studied in module 2. Moving on to module 3, my module 3 is basically a combination of two parts. So first part is all about the study of combinational circuit design and simulation using gates, and the second part of my module 3 includes multiplexers, decoders and PLDs, or what we call it as programmable logic devices. So basically it's one and the same. So what we are doing in combinational circuit designers, we are going to check out how the circuits or how the gates what we have studied in the module 2, that is your, it may be a basic gate or it may be universal gate, how do we connect them together, and after we connect them together, what are the different circuits that can be formed. Once the circuits are formed, we need to check whether they perform properly. So basically what I do here is I'll be rigging up a circuit, I'll be checking whether they works fine. But in the practical world or in the reality, what I do is I'll be initially going with the design part, and once the circuit has been designed, I'll be going with the simulation using a software package, and once my simulation results are fine, then I'll come to the combinational circuit design. So initially I'll be going with the simulation part and later I'll be coming on to the circuit design. But as a part of the curriculum, what we'll be doing is we'll be checking on the circuit design initially, and once the circuit design is known to us very properly, then I'll be going on to know that how we can be writing the code corresponding to that particular circuit. So this is what we are going to do. Moving on further, that is in the second part of module 3 or in the second chapter of module 3, we will be studying about multiplexers, we will be studying about decoders, and we will be studying about programmable logic devices. So thus multiplexers, decoders and programmable logic devices are basically combinational circuits itself. So we will be checking the application part of the combinational circuit design in the second chapter of module 3. We'll check out what are the things that are included in this particular module. So moving on, we have the syllabus blow up is given here. So it includes review of combinational circuit design. Review of combinational circuit design means how basically we'll be checking on the previous things, what we have studied, and how are we going to apply them in the design of the circuit. After the review has been done, we'll be directly getting into the design of the circuits with limited gate fan in. Here the term fan in refers to the number of inputs. What are the number of inputs that I'm going to give to that particular circuit? So technically we call it as gate fan in. After that we'll be checking about gate delays. Gate delays means the timing delays what occurs in the circuit once it has been rigged up together. Also the schematic representation of those particular time delays using timing diagrams. Later we'll be checking on the various hazards that a combinational circuit or combinational logic circuit will be facing, and finally we'll be going on to the simulation part, and after the simulation part we'll be testing the logical circuits whatever I have rigged up. This is what I said you initially. I need to go on with the simulation, and only after the simulation has been done I can go with the practical circuits. So this is my first part of my third module, or you can call it as chapter 1. This particular thing can be called as first part of chapter or first chapter of module 3. Moving on further, moving to the application part of the combinational circuits, we'll be looking into multiplexers. We'll be checking out what are multiplexers, what are the different kinds of multiplexers, how do we design the multiplexers, what are the ready-made multiplexer ICs available. After that we'll be checking on 3-state buffers. Later we'll be checking on decoders and encoders. After that programmable logic devices, under which we'll be checking PLAs and PALs. So this chapter 2 of your module 3 is entirely application part. So in the initial part, we'll be checking on the initial circuit design, and later we'll be using that particular design for the application part. So this is the brief syllabus blow up of your module 3. Fine. We'll be directly getting into the combinational circuit design and simulation using gates. Now, to begin with, let's say that I need to design a circuit. You people are given with the problem of designing a circuit. So how do I design or how do you design a circuit? So normally what I'll be asking is, I'll be giving you a function. I'll be giving you a function which may be of the form f of some variables equal to something, or I may be giving you the problem something like this: y is equal to some variable combination. So once this particular problem or once this particular design is given to you people, how are you going to solve it? The initial thing what I'm going to do here is, I'll be drawing the truth table. I'll be drawing the truth table for the given problem. So this is my initial thing. Once the truth table is drawn, I'll try to get a simplified equation, or I'll try to get a simplified expression from the truth table. Maybe I can be using K-map. I might go with the K-map, or I might go with the QM method, or I might go with the Petrix method, or any one of this, that's up to your comfortable level. Which method are you going to get, so that you land up with the simplified expression, or you can call it as simple form. So I need to be getting a simplified expression. Once this expression is obtained by you people, once this expression is with you people, so what is the next step? The next step is all about designing the circuit. Designing in the sense, designing is already done. I need to implement it. So initially what I'll do is, I'll try to implement the given expression using, maybe I'll go with the basic gates. I'll be either going with the basic gates. And if you are good with the simplification rules and laws of my logic design, then probably you can upgrade your circuit which was rigged up using basic gates using universal gates. You can rig it up using universal gates also. So this is how you design the circuit. So these are the brief step what you follow in order to design a circuit. You know what is the output you are expecting. Once you know what is the output you are expecting, you will try to write that particular problem in terms of the truth table. You try to simplify it. After you simplify it, you will go with the implementation part. So once this implementation part is done, you will be able to rig up the circuit using basic gates or universal gates. So when I speak about basic gates, I may be rigging up the circuit using AND or combination, or I may be going with OR and combination. This AND or combination circuit occurs if I am using SOP method. Suppose if you go with OR suppose if you want to rig up the circuit using OR AND, that is input to be given to OR gates and the output to be obtained from the AND gate, then probably I will be going with the POS method. I do agree that both the things will be having NOT gates. In case if it is needed. So if the NOT gates are needed, I'll be embedding them in the circuit as it is needed. Once you get a circuit which is made up of AND OR combination or OR AND combination, it is possible for you people to reduce this circuit to a combination which is made up of only NAND circuit. You can reduce it. You can rig up a circuit which is made up of only NAND combination. Or you can also rig up a circuit using NOR combination. So this is possible. So what I mean to say overall is, your circuit may be either an AND OR circuit, it can be an OR AND circuit, it can be a NAND NAND circuit, or it can be a NOR NOR circuit. So the circuit whatever you are going to rig up can be any of this particular combinations. It can be any of this particular combinations. But you need to make sure that you need to be selecting the inputs. You need to be making sure what are the number of inputs that are to be given to the circuit, and how should be your output, So these two things should be known to you people before you actually rig up the circuit. Once you know what are the inputs and once you know what are the outputs, you can rig up the circuit using any of this particular combination. After the circuit has been rigged up using any of this particular combination, let's say that my circuit has been rigged up using these four combination, it is not that that circuit will be a finalized one. It is not that the circuit whatever you have drawn will be a ultimate or it will be a unique circuit. It is possible to reduce it. You can reduce this circuit, to any of the format. For example, if your circuit was rigged up using AND OR combination, let's say it is rigged up using AND OR combination. But looking into AND OR combinations, you feel that number of gates in this particular circuit are comparatively more. And now what you want to do is, you want to reduce it to a circuit which is having a minimum number of gates. So what you can do is, you can reduce it to a circuit which is having NAND NAND combination. I am not sure whether my NAND NAND will be giving minimum number of things, but it is possible to reduce it. So any of the forms can be reduced to any of the forms, from here to here or from here to here. From here to here you can either reduce it or you can go from here to here. That's up to your choice, which form of the circuit you are looking into. Yes. See, this is what I said. Steps involved in the design of a combinational circuit. This is what I explained to you. Set up a truth table, derive simplified algebraic expressions using any of the methods, reduce the total number of gates and inputs. That is, at the input side, you need to reduce the number of basic gates and the gate inputs. Why should I reduce the gates and gate inputs? This particular method is done in order to reduce cost and power consumed and space. So I'm going with the second method in order to take care of these things. I need to be having, if I go with less number of gates, the cost of the circuit will be less, power consumed will also be less, and the space consumed will also be less. After that, you realize it using SOP or POS method. That's what I said. If you are going with SOP method, your final circuit will be of AND OR combination, or if you are going with the POS method, it will be of OR AND combination. As I said you, this is not ultimate. You can interchange it. You can, if you rig up a circuit using OR AND combination, and if you want to write it using AND OR combination, you can write it. Or you don't want to write it using any of these combinations and you want to write it using NAND NAND combinations, that is also possible. You can write it using NAND NAND combinations also. This is what the steps are explaining here. This particular step has been explained to you previously also. In the previous method or in the previous slide, I have explained you how the particular circuit will be rigged up. The same has been given in terms of points. Okay. Design of circuits with limited gate fan-in. Now, not to confuse with you people, this gate fan-in is a technical term for what I call it as inputs, or you can call it as logic inputs. So as explained, when you go for the practical designing of the circuits, that is when you go for the reality of the design, normally the number of inputs what can be given to the circuit is always limited. It is not that you can be giving any number of inputs to the circuit. Always you take a circuit, any circuit you take, let's say that you take a circuit here, let's say this is your circuit. The number of inputs whatever you are going to give to the input side will always be limited. It is not that you can be giving any number of inputs. And this number of inputs whatever you are going to give may be limited to 2, 3, 4, 8 or maybe some other number. But always always think that it is not going to be infinite. It is always having a limited inputs. So this inputs whatever you are going to give to this particular circuit is called as limited gate fan in, or you can call it as limited logic inputs also. Now, what might happen in some circuits is there may be multiple levels of realization. Let's say that is gate 1, this is gate 2, and this is gate 3, and finally this is gate 4. Let's say this is gate 4. So you are giving the input from here, and that has to be coming to the second gate, and that output has to be coming to the third gate. From the third gate, it has to be coming to the fourth one, and the fourth one you are going to get the output, or that is Y. What you call it as Y. Now this number of gates, whatever I have here, this is 1, 2, 3, and 4. It is possible to reduce the number of gates or number of levels of the circuit by using some of the basic laws or basic rules what I use in my logical circuit. So that is what it is given here. Factoring the logical expression to obtain a multi-level realization is necessary. Normally what happens is whenever there are multiple circuits or multiple gates connected in the circuit, let's say that there are some gates connected here, there are some gates here, here and here. Suppose you say that, sir, the number of gates in the circuit seems to be pretty more, then it is possible for you to factorize it. Then it is possible for you to reduce the number of gates that are present in this particular different levels of the circuit. So what I need to do is I need to be designing the circuit. Always you keep in mind, whenever you are designing the circuit, first thing what you need to know is you need to be asking yourself, sir, what are the inputs that I need to give to the circuit? Because based on the number of inputs that are going to give to the circuit, the number of gates at the input side will increase. Suppose if you are having, let me say, some 8 or 9 inputs at the input side, number of gates will obviously increase. Suppose if you are having minimum number of gates at the input side, the number of gates will obviously be less. That is what this particular topic is all about. See here what they have given us. They have given you an expression. I am not going to solve it. They have given you an expression which is to be solved using the SOP method, but they said that using 3 input NOR gate. So they are very much precise and specific, saying that I don't know how are you going to solve it, I don't know what circuit you are going to rig up, but make sure that your end circuit will be made up of 3 NOR gates. It should be made up of 3 NOR gates. This is what they are specifying very clearly. So as always, what are you going to do is, as I explained, you are going to take a truth table. After the truth table, you are going to take a K-map. So normally an easier method when there are 4 variables. After K-map, you are going to group them. After you group them, you will be getting an expression. And once the expression is obtained to you people, you will try to deduce the expression to a simpler form. And after the expression has been deduced, you will try to rig up the circuit. But what they said is, make sure that the circuit whatever you are rigged up, when it comes to the very final stage, it is made up of only NOR gates, or it is made up of using 3 input NOR gate. It is not using only 3 NOR gates. They are saying that at the input side, make sure that there are only 3 NOR gates. This is what they have clearly specified, which means that they are saying, they are giving you a gated fan in, or they are saying that at the input side where you are going to give the input, keep only 3 input or keep only 3 NOR gates. That is what they are specifying. So grouping has been done, and once the grouping has been done, they have obtained the final expression. See, they have obtained the final expression as it is given here. After the final expression has been given here, see, if you look into this particular final expression, what is given here, I am pretty sure that it is not possible to go with the condition what they said. The condition what they said is, they want only 3 NOR gates to be connected at the input side. But as per the expression what I obtained here, I feel that it is not possible to go. See, this is something like this. I'll be getting something like this. This is what it is obtained. See here, this is what they got. So using 3 NOR gates, it is not possible to design the circuit. So what they did is, they used some reduction formulas and reduction laws, and finally they reduced this particular equation. And using this particular equation, you can check out at the input side, there is 1, there is 2, and there is only 3 NOR gates as per the condition. Intermediately, I don't mind. This comes to be the second level, this comes to be the third level, and this comes to be the fourth level. But in the first stage or in the first level, they have rigged up a circuit which has got only 3 input NOR gates. So normally they might ask you, or they might give you a numerical, and they might give you the condition. Make sure that your final circuit is made up of a limited number of NOR gates, or it is made up of limited number of NAND gates. Suppose if they give you this particular condition, then you need to be applying the rules and laws of logical reduction, and you need to come to the simplified expression which will be satisfying the condition. And once this condition is satisfied, only then you can come to this particular circuit. Because you can check out, as per the K map, they got this particular expression. As per this expression, I don't think I would have been able to rig up the circuit using 3 input NOR gates. So what they did is, they deduced it. And after they deduced it, they got the circuit which is made up of 3 input NOR gates. So this is your first stage, this is your second stage, this is your third stage, and this is your fourth stage, which means that there is 4 level of realization. So I don't mind whatever is the level of realization, but what I mind here is, I mind about this condition, 1, 2, and 3 input NOR gates. That is what this topic is all about. Design of the circuit with limited gate fan-in. At the input side, they are going to tell you, see, this is what I need at the input side, and these are the gates what I need at the input side. So that is what this topic is all about. But normally what happens is, even though I have explained this particular topic in detail to you people, normally my design using this particular condition, or using limited gate fan-in is normally not used. Because most of the times it is not possible to deduce them using the conditions given. Most of the times it is not possible. Maybe it is possible at some point, but most of the times it is not possible. Whereas it is possible to ask you people to say that, realize the expression using only NOR gates. Or realize the expression only using NAND gates. This is possible. You know why this is possible? Because both these gates are universal gates. What you used to do was, you would have rigged up the circuit using basic gates. Now what you need to do is, you need to replace this basic gates by NAND or NOR gates. This is possible. But a circuit design using the limited gate fan-in, most of the times it is difficult. Until and unless you are a pro in this particular procedure, you can go with this. Beyond that, it is not possible. So the importance what I give to this particular topic is around 5%. I don't give a lot of importance to this particular topic. Normally, this topic is of that importance to the people who work with the logic circuits in the real world or in the industries. Because in the industries, they will surely say, yes, I want a circuit with only NOR gates at the input side, with only NOR gates at the input side, with only NAND gates at the input side. Industry level or in reality, it is possible. But coming to the academics or coming to the curriculum, it is a bit difficult. It is not that it is completely not possible, but it is a cumbersome task. Moving on further. Gate delays and timing diagram. So what do you mean by this gate delays? Gate delays is nothing but, what do you mean by delay? You say that, sir, my bus is delayed today. What do you mean by delay? Delay is actually you had to reach at 9 o'clock, but you reached at 9:05, which means that there was a delay of 5 minutes, isn't it? Which means there was a delay of 5 minutes. Very similarly, when I speak about the circuit, let's say this is my circuit, and you are giving some input. Let's say that Vi is the input. You say that Vi is the input. You are giving the input at 0 second. You are giving the input at 0 second, let me say. As soon as you give the input, your circuit should produce the output. Now, can you expect your output also to be coming at 0 second? Can you expect your output also to be coming at 0 second? No, it is not possible. It is not possible. Maybe it will take somewhere around nanoseconds of time. It might take some around nanoseconds of time. This nanosecond time, what my circuit is taking in order to produce the output is called as gate delay. The delay that is produced in the circuit due to the gate is called as gate delay. When the input to the logic gate is changed, the output will not change instantaneously. When I give the input, I need not or I cannot expect my output to be changing instantaneously. The gate takes finite time to react to the change in the input, so that the change in the gate output is delayed with respect to the input change. This is what is meant by gate delay. I know this gate delays will be in terms of nanoseconds. Okay, it will not exceed this. It will be in terms of nanoseconds. But when I speak about combinational circuit, let me write here. Let me write here. I have one circuit here, one gate here, one gate here, and one gate here, and one more gate here. Let me say this is my circuit. This is my circuit. So my output has to pass through all the stages. Suppose you say that this is producing some nanoseconds, this is producing some nanoseconds, same here, and same here. So when I give the input from one end and when you get the output, normally there will be time delay. Normally there will be time delay. So when all these time delays combine together, they might sum up to be some value. Even though they are in terms of nanoseconds, they might be summing up to be a particular value. This particular time taken by the circuit in order to produce the output after the input has been injected to the circuit is called as gate delay, or you can call it as time delay. And what are these timing diagrams? These timing diagrams are nothing but representation of the time delays. So your circuit will be having the time delay, and those time delay has to be represented, right? You people should be able to understand, yes, this is a time delay. This is how I am going to represent it. So that is nothing but your time delay. That is what is your timing diagram. See here, I have a circuit, you give the input. That input is represented here. Please concentrate. That input is represented here. That input is represented here. Input is represented here. Now, as soon as you give the input, let me draw it here, okay? Let me draw it here. Let me draw the output. Let me say this is Vi, this is V0, yeah. You can concentrate, you can see that at this point, you have changed the input. You have changed the input from 0 to 1. You have changed the input from 0 to 1. When you change the input from 0 to 1, please concentrate. When you change the input from 0 to 1, your input has already changed. Or let's say that, let us draw it here like this. Let us draw it like this. This is your input. Let's say this is your input, okay? So this is where you have changed your input. This is where you have changed the input. Coming to the output, my output will change at this particular point. It will change at this particular point. So it had to change here, but it will become 0 as it is a NOT gate at this particular point. So this particular time duration what I have, this is called as time delay. This is called as gate time delay. You can observe here also. Your input is becoming 0. Your input is becoming 0. In spite of your input becoming 0, your output is becoming 1 after a particular time gap. You can observe that, right? You can observe this particular time gap. This particular time which is taken by the circuit in order to change the output with respect to the input is called as time delay. Yeah, this time delay will be in terms of nanoseconds. But when I speak about combinational and sequential circuits, normally this time delay is of prime importance to me, because there will be multiple gates connected. So all these nanoseconds will combine together with each other, and they might be producing seconds of time delay. So I don't want this time delays to be growing bigger and bigger. But keep it in your mind, these time delays are unavoidable. You cannot avoid it. That is why I said, try to reduce the number of gates in the circuit. More the number of gates, more the time delay. Suppose if you have lesser number of gates, lesser will be the time delay. And what it is represented here, this is all about some simple diagram. So you have your input is 0 here, right? Your input is 0. And you try to make your input 1. As soon as you try to make the input 1, your input will not drastically become 1. It should have become 1 at this point itself. But it has not become 1. It is taking some time to become 1. This particular time delay is called as rise time, or you can call it as rise transition time. Similarly, your input is 1 and you want to make it 0, but as soon as you try to make it 0, your input is not becoming 0, it is taking some time, and that particular time is called as fall transition time. This is all it is. See, it is explained here. Rise time is time taken for the input or for the output to rise from 10% to 90%, 10% to 90%. Similarly, fall time is nothing but the time taken by the input or output to fall from 90% to 10%. So that particular time duration is called as rise time or fall time. Basically, it's a time delay or gate delay itself. Fine. Let's take one example. Let's take one example. So I have one gate here. This is my first gate. This is my second gate. Assume that each gate has a propagation of 20 nanoseconds. Okay. Let's say that this has got a propagation of 20 nanoseconds and this also has got a propagation of 20 nanoseconds. This timing diagram indicates what happens when the gate inputs B and C are held at constant value 1 and 0 respectively, and the input A is changed to 1 at t equal to 40 nanosecond and then changed back to 0 at t equal to 100 nanosecond. Basically, this diagram is all about the indication of the time delay. See here, this is your input. A is your input. A is your input. When you are changing the input at the input side, if that input has to be reflected at the output of gate 1, if it has to be reflected at the output of gate 1, how much time duration it has to take? It has to take 20 nanoseconds. Can you see it here? Can you see it here? It is taking a time gap of 20 nanoseconds. That is what it is happening here. Similarly, if the same has to be reflected at the third gate, or if it has to be reflected at the gate G2, how many time duration it has to take? It will take 20 plus 20, which will be 40. So can you see that? 20 here and 20 here. So totally, for the input to be reflected at the output, it will take a total time duration of 40 nanoseconds. This is what they are trying to explain you. Similarly, you try to reduce the input. If that input reduction, if it has to be reflected at the output side of the gate 2, it will take 20 plus 20, which is nothing but 40 nanoseconds. So this is what they try to explain. So every gate will have its own time delay. It need not be 20, it need not be, or it is not a fixed value. It can have a different values depending on the material what has been used in order to manufacture it. So this is what is about propagation delay or gate delay or timing delay. So a circuit is given, the time delay is indicated using what is this? This is your timing diagram which gives you a clear-cut idea regarding what are the changes in the input and how long the output is taking to change.